Right, let's talk about linked lists. Woo. So on Monday, we talked about the structure of a linked list. We went through some memory diagrams, and we saw how a linked list is actually just a series of nodes that know two things and two things only, the value at that node and a reference to the next node. So let's expand on that and look at some implications of this and really how to work with these things. To start, we got to talk about generics. So just a few slides at the beginning. I got to get generics out there. We got to know what these things are. So we built this linked list node last time, this linked list node int, and it's fine. It's a linked list. It gets the point across of what a linked list is, and we got to see references and a whole bunch of this in our memory diagram. But it can only ever store ints. That's way too restrictive and not very useful for what we want to do. If we're creating a data structure, we would like a data structure that can store anything. We want to store anything in these things. We don't just want a data structure that stores int for a lot of reasons. One thing, what if we want to store anything else? Anything else? Are we going to create another class for that? A linked list node string, a linked list node double. And for your homework, am I going to have you write a linked list node rating and just add all these linked lists up? No. No way. We're not doing that. And array lists don't do this either. That's not how we use data structures when we're on the other side, when we're just using data structures. With array lists, there's one array list class, and whenever we create an array list, we tell it what we want to store in that array list. For this array list, we didn't just say, give me an array list. We said, give me an array list of integers. And this array list is going to store integers and integers only. If we want an array list of string, we just give it string here. If we want an array list of rating, we just give it rating there. We would like the same thing in our linked list, right? It's pretty handy to have. I just want to write one linked list and have it be able to use for anything. So let's do exactly that. We're going to rewrite our linked list node class to use a Java generic. I usually call these type parameters. In Java, they're called generic, so I'll stick with the Java terminology. But we have a Java generic, which is going to be a variable that stores a type. Usually our variables just store values. This variable is going to store a type. And when we have these variables that store types, it's common convention, not exactly sure why, but it's common, and I'm not complaining about it, I actually like it. It's common convention to have these variables be one uppercase character names. So just capital T, that's our variable for our generic. So we're setting up this class to be able to take in a type as a generic and store it in this variable T. So we have, to specify that, to say this class takes a generic, we're going to specify that with angle brackets right after the name of the class. So the name of this class, linked list node, and then in angle brackets, we're going to specify the variable for the generic that's going to store that type when we actually start creating objects of type linked list node. We create an object in the class. This is a variable, and objects. That variable is going to be a specific type. That's going to be the type of that specific linked list node. So this is the syntax to say this class takes a type parameter, and then whenever we need a value of that type, we're going to use t instead of whatever the type would be. In our previous example, this was int in both these cases, in both these spots. Now we have an instance variable that stores a value of type t. We just say t for the type. We use t in place of whatever the type would be. The constructor takes a value of type t, so we say the type of that value is t. So we're going to generalize what the type is just by replacing the type with t, and then letting whoever creates a linked list node object, let them decide what t is going to be. When we have a linked list, we very, very strongly should, all the nodes in a linked list should have the same generic, the same type T in this case. So when we have our reference to next and our constructor that takes the reference to next, those should both be a linked list node of type T. So we specify our type parameter in those variable names to say this is a link, not just a linked list node, but a linked list node of type T. The type parameter, the generic type is T, which is whatever it is here. It's just going to be the same thing. Technically, you could create a linked list where the type changes as you go node to node, but that's not super useful. So we're going to stick with the same type all throughout our list. So we have a linked list of type T, not a linked list with nodes of different types. Just stick with T for all of our nodes in the same list. And then when we create a linked list node variable, we're going to specify what the generic type is. So in this linked list node, we're going to specify the type of integer, just like we did with Arraylist. We're just seeing the other side of the coin on that. This is how Arraylist sets this up, which we briefly saw in the Arraylist code. And I kind of glossed over it because it's a topic for today. When we create a variable of type linked list node, we're going to specify the type parameter. So this is a linked list node of type integer because I'm specifying it's going to be integer right here. So we're effectively passing the type of integer to the type parameter. This is why I like type parameter instead of generic, but to the type parameter or generic T. So we're assigning T to the type integer. So for this linked list node, every instance of T here is effectively integer. But that's set for each object. So just like I can have in the same code an array list of strings and an array list of integers, I can do the same thing with my linked list node because it's on a per object basis. So I can create a linked list node of integer in this case. I could create a linked list node of string if I want to, just by changing what the generic type is. So in this, when this is my code for this specific linked list node object, all of these values of T are effectively string. So whenever you see T, that's just taking the place of a type that's going to be specified when somebody creates an object of this type. In the class, it's just T. It's all generalized out. It's all generic, if you will. But when you create objects of this type, it's going to be a specific type for that object. And when we call the constructor, you can, in these angle brackets, just like for Arraylist, you can specify the type again. You can put in integer in between these two angle brackets. This is the one of the few cases where Java actually lets us shortcut things. So we can just do our angle brackets and not specify the type. You do have to have these here, but Java will see we're storing this in a variable of type with a generic of string. So it's going to say, yeah, this is going to be a linked list node of strings. So we do get to cut that short in the constructor calls, but in our variable types, we have to specify the type parameter. So this is a linked list node of string. Doesn't make sense just to create a linked list node. We create a linked list node of something. In your homework, right when you get to the first method in task 3, you're going to create a linked list node of rating. I almost blanked on it. Of rating. You're going to create a linked list node of rating, which is going to be stored in an instance variable in your song class. So a little bit of moving pieces, but the generic is a placeholder for a type, which will be specified when we create an object of that type. This lets us write code one time. We write one linked list node class, and it can store values of any type, even types that don't even exist yet. When the Java developers wrote the Arraylist class, they didn't know that we were going to write a rating class with the instance variables that we had. They had no idea that we were going to create that class. That type did not exist when they wrote the Arraylist class, but we can still create an array list of ratings. Same thing with this. We want the same functionality here. Same thing with linked list node. I want to write this code one time and one time only. I don't want somebody saying, hey, I just created a rating type. You mind creating a new linked list for my new type so I can store this in a linked list? No, I don't want to do that. Every time somebody comes up with a new type, that ain't happening. So we write this code one single time, and it can be used with any type ever. asterisk, except for generic types. So any type in Java except generics. Hold on, my brain. Any type except primitive types. So primitive types can't be type parameters. This is why in ArrayList we couldn't say ArrayList of int. We had to say ArrayList of integer with a capital I, because we can't use primitive types as our generic type. That's the only exception. Other than that, every single type in Java that's defined by a class is a valid type parameter, even if the class didn't exist when we wrote our code. This gives us a lot of flexibility in our data structures. So any questions on generics before we get into algorithms? The rest of the lecture is going to be quite a bit of rapid-fire algorithms for linked lists. Double.min value. I don't know if any of y'all were part of that conversation, but double.min value that caused me hours of debugging one day. I'm still mad at that. Maybe I can save y'all some hours down the road. Double.min value is a constant, which is the minimum value that can be stored in a double. It is not the minimum negative value that can be stored in a double like I thought it would be. I thought it would be a really, really large negative value. What it actually is the smallest positive value that can be stored in a double. So it's not quite zero. It's just a smidge bigger than zero, which wasn't what I wanted for my application. I wanted a really big negative number. So it's not the minimum value that can be stored in a double like the name implies, min value. And min value for an integer is the largest negative value. So of course I would think double.min value is the same thing. But no one came up with a question during my rambling? I'm moving on then. Let's move on to algorithms. Okay, so we want to add some more functionality to this linked list. We got our generics set up. We have a linked list that can store any type, including rating, which is very relevant for the homework for task 3. So now let's start adding some actual functionality on this. Let's start with our getters and setters. I'm going to create my getters and setters that I need for the value and the reference to the next node. And this didn't come up last time when I introduced getters and setters. I just created them all because I was just focused on the topic of getters and setters. When we use getters and setters from here forward and in the real world, you only write the getters and setters that you're going to use and that you're going to need. So in this case, I don't want anybody to set the value of a node, so I'm just not going to write that setter. So notable omission here is set value. It's not existing in my getters and setters because I don't want that functionality. I don't want people to be able to change the value of the node. This will become more important when we get to trees. Trees are also node-based data structures. And we don't want that value changing from us for our specific application that we're going to have. In task 6, programming task 6, you're going to be using a tree to sort songs. And if you have all your values in sorted order, and somebody decides to take one of those nodes and change the value and put a different song there, it's going to mess up our whole sorted order. It's not going to be sorted order anymore. So we want to make sure that we avoid that. Now that I think about it, they could just get the song reference and call set title and set artist on it, but we're not going to be perfect. But we're going to try. I can't change that now because program task 2 has already been out there for a while. A lot of y'all have finished it. Got the expected deadline this morning. So we're only going to write the getters and setters that we want people to be able to access. I'm not going to let people set the value, so we just don't write that setter. We do want them to be able to update and get the next node, so we'll write that getter and setter so they can manipulate the list, they can change the references and restructure the list all they want, and get value, the most useful one. If we're going to have a data structure storing data, we want people to be able to get that data. It's kind of essential there. So that's our getters and setters. Now we want to talk about 4 algorithms. This is the rest of the lecture. We want to talk about these 4 algorithms. Size, get the size of the list. Append, add an element to the end of the list. Find a specific value. And the biggest one of these 4 is going to be min. Find the min value of a list of doubles. So the first three, I'm going to rip through fairly quickly. It's going to be a healthy clip. I'll stop for questions, of course, and reinforce the content. But I'm going to go fairly quick because I want to make sure I get to min, because min is going to be the most relevant for your homework assignment for task 3. But the main question that we're answering here is, how do we work with a linked list? We have the structure down. Cool. We saw toString. We got a little functionality there. But how do we work with these linked lists and actually use them to get stuff done? So let's start with these 4 algorithms to get that stuff done. So size, just count the number of nodes that are in the linked list. Now, for an array list, this is easy, right? An array list, it was a while ago, maybe you don't recall, but an array list has an instance variable of type int called size. You get the size of an array list. The array list just says return this dot size. Done. That's it. That's all it has to do. And then it has internal functionality to keep that variable up to date, make sure it is the actual right size of the array list. A linked list can't do that. I mean, technically we could. We could technically write code that does that, but Append could increment that value and stuff. But we're not going to do that. That's not how we roll with linked lists. But a linked list can't do that. If we ask the head of a linked list, the first node in a linked list, and we say, what's the size of this list? It doesn't know. What's a linked list node know? Only 2 things, right? It knows the value stored at that node and a reference to the next node in the linked list. It doesn't know its size. It doesn't even know anything about the rest of the linked list. It just has a reference to the next node. Period. That's it. That's all it knows. So we can't just ask the first node for the size. We got to do some extra work. So, and we're going to see more recursion today. All these algorithms are going to be recursive. We're going to do this in 2 checks. There's 2 different things we'll do when we ask a node for its size. One, if the node is the last node of the list, if it checks its next reference and it's null, it knows how big of a list it refers to. It's a list of size 1. Now, each node doesn't know anything about the previous nodes. The last node in the list doesn't know that there's a rest of a list that refers to it. All it knows is itself and the next thing. So effectively, the last node in a linked list is a list of size 1. Because it doesn't care what refers to it. In fact, it could be the last node in several different linked lists. You could have 8 different nodes that all refer to it as its next value. Technically possible. It is a linked list of size 1. So it's going to return 1. My next is null. I'm 1, so I must be a linked list of size 1. The other case is if we're not at the end of the list. If we're not at the end of the list, each node is going to ask the next node for its size and say, hey, how many elements come after me in the linked list? It's going to ask that next node, say, hey, what's your size? And it's going to wait patiently for an answer, and then when it does get the answer back from that node, it's going to say, well, if you're linked list of size x, I am a linked list of size x plus 1. So it's just going to add 1 to that and then return to whoever asked it for its size, which might be another linked list node, or it might be the person who actually called the initial size method, not a recursive size method. And of course, this is recursive. And since we're calling size here through this dot next, in that next stack frame of type size, this is going to be the old this dot next. So we're updating the reference of the node we're looking at through the references of this. So each time this dot next go into the heap, move over to the next element, the next node, and then call size. So for that stack frame, size is the next element, next node in the linked list. So we're taking advantage of this, and we're not going to have time in lectures, and a lot of lectures from here forward. We're not going to have time to do the full memory diagrams. I'm going to do a little visual and kind of do a very abbreviated diagram. At this point, we've been seeing memory diagrams with references in this for a bit, not a tremendously long period of time, but a week and a half. I'm at the point where I'm going to start assuming that you get the idea of this stack frames references. We've seen it enough. If you're lagging behind on that, go watch the old videos, watch the old lectures, study up, and make sure you understand how those references work. I'm not going to have time, unfortunately, in lectures anymore to go through the whole stack trace, the whole memory diagram, and show you how these this and the references all move around in memory. But we've seen enough of them. Even with linked lists, just seeing the toString, you can expand that to any of these and draw your memory diagrams for practice with any of these algorithms. I'm going to do these quick abbreviated memory diagrams with just quick visuals. So when somebody calls the size method, they're going to ask the head of the linked list, hey, what's your size? How big of a list are you? That node doesn't know. It says, I don't know. I don't know how big of a list I am. I only know two things, my value and a reference to the next node. So it's going to do one check. It's going to say, am I the end of the list? Nope. So it's going to ask the next node. It's going to say this.next.size. So it's going to put a new frame on the stack where this is going to be a reference to this node. And this node's going to do the same check. This node's going to check, am I the end of the list? Well, next is not null. So let me put another frame on the stack, this.next.size. Put another frame of size, another recursive call to size on the stack at this node as this being a reference to this node. And this node's going to do the same thing. It's going to check, and it's going to say, whoa, looks like I'm the end of the list. I got no one to ask for their size. So this node, this.next, is null. It realizes it's the end of the list, and it's just going to return 1. I'm a linked list of size 1. And it effectively is. We effectively have 3 different linked lists here. 4 if you count null as being an empty linked list. We have a linked list of size 1, a linked list of size 2, and a linked list of size 3. There are 3 linked lists here. The first linked list node happens to refer to the node representing a linked list of size 2, and that one refers to the linked list of size 1, but this last node is effectively a linked list of size 1. So it returns, I'm just size 1, just me here. My next is null, it's just me. This node gets that response from the last node, and it says, well, if I refer to a node representing a list of size 1, and I myself am a node, let me just bump that up by 1 and return 2. The first node, the head of the list, gets that value. It gets 2. It asks the next node, hey, what's your size? And it waited a while. There were frames that went on the stack and stuff that happened. But it eventually got the answer of 2. It bumped that up by 1 to count itself, and then returned 3. And then whoever called this method got the value 3. It says, cool, all right, that's what I was looking for. I just want to know your size. I don't know why you did all that recursive stuff and went down the stack and up the stack. But I got my answer. My answer's 3. Thanks. So when it comes to recursion, with linked lists especially, this is going to be the common pattern. We're going to see this quite a bit today as well. This is going to be the common pattern. You're going to check if we're at the end of the linked list. If we're at the end of the linked list, this is called our base case. This is where we're going to run some code that does not make a recursive call. In this case, and it's usually a trivial answer to return. If I'm at the end, if next is null, I'm at the end of the list, and that's just a list of size 1, so we return 1. So you're going to check, am I at the end of the list? If I am, just do something simple. There shouldn't be too much to be done there. If I'm not at the end of the list, I'm going to run my else, and that else is going to contain a recursive call. We're going to ask the next node a question. The answer comes back. We're going to assume that it gave us the right answer, and then we're going to do just a little bit of work to build up the answer by a little more. For size, whatever the size of next is, plus 1 that, and then return it. Now, if this is a list of size 1,000, we're going to put 1,000 frames on the stack. The last one's going to return 1, and then all the rest are going to just add 1 to that, and we're going to end up returning 1,000. But each stack frame, each method call, doesn't do much work. So when you're writing your recursive methods, it kind of feels like magic sometimes. You're not writing all that much code. We wrote return 1 or add 1. That's the only 2 things we did. But by having a lot of frames on the stack, each frame doing a little bit of work, the combination of all those frames, all adding 1 in this case, get us to the full size of the list. So for linked lists especially, checking, am I at the end of the list or not? That's almost always your check. If I'm at the end of the list, base case. If not, recursive call. Why did the nodes have values 4, 3, and 1 in this example? That's just the numbers I picked. I was getting sick of 3, 2, 1, so I changed it to 4, 3, 1 in this example. I don't have the main method written here, but it would be create a node with 1 next of null, and then create a node with 3 next of this node, then create a node with 4 and next of this node, and then store a reference to this node in a variable in the main method. Net size. These are going to go rapid fire. I want to get quickly to min and then slow down when we get to min. Min's a bit more complex. Yep. What was that? Sorry. It's just counting the number of nodes. So since we have 3 nodes, we expect it to return 3 when we ask the head of the list its size. Just like with an array list, asking an array list its size, like how many values are contained in here. We're not checking the values themselves at all. We don't even say .value anywhere in here. So we're just strictly counting the number of nodes in the linked list. Yeah. No. So 2 questions. Is there a faster way to do this? Not really. Unless you have some bookkeeping overhead, you could keep track of that. Like whenever a value is prepended or appended, you increment it, and then if a value is deleted, you decrement. You could technically do that. We usually don't with a linked list. If you're doing something like that, we just use an array list instead. So can we speed it up? Not really. Do we need to? And the second question: do we need to care about performance in this class? No. 116, we're the progression, in my mind, the way I like to look at it, 115 is getting things done, 116 is how things work, and then 250 is going to be, and really the rest of the curriculum for 4 years, is efficiency. How do we get things done fast, efficient, optimal? That doesn't start till after 116, though. We don't care about efficiency. I don't care if your code's slow as hell. As long as it doesn't time out in Autolab is the only thing, which is several minutes. The only way to realistically do that is to have something really bad in your code, usually going infinite. If we never hit this base case, and I've seen this a bit in task 1, the sum of digits, writing that while loop, and the condition is always true. You go infinite and you time out in Autolab. So things like that, of course. And when we get to file I.O., sometimes you can do something really sloppy with file I.O., like reading a file with 100,000 lines 100,000 times. That will time out in Autolab as well. Other than those things, I don't really care about how fast things run. In 250, you will. So 250, like size here is called an O of n operation. It's linear time. In 250, that'll be a big deal. Append. So we saw prepend. We kind of saw prepend. We just did it in our main method. We could write a prepend method in our linked list node class. Kind of. But append, we're going to write. This is going to append an element to the end of the list, which is what we expect from array list. When you call add on an array list, we get it added to the end. And it's what you need to use on your homework. Right from the first method that you write in your homework, the add rating, that's going to add it to append to the end of your linked list that you're storing in an instance variable. So append, this is something that we want to use. Append to the end of the list. So we have 2 goals here. First, find the end of the list. And then once we reach the end of the list, we're going to create a new node and then refer to that, and that's the new end of the list. So we're either at the end of the list and we update our next, instead of being null, we update it to be a new node containing the value that's being appended, or we're not at the end of the list and we just move down to the next element. We say, hey, this dot next, hey, my next node, call the append method with this being that next reference, and then just move down the list that way by updating this is going to be the next node, next node, next node. We're saying .next, 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 .next until we reach the end of the list, and then adding the node there. So somebody wants to append to this list. First node says fine, but my next isn't null. So I'm just going to tell the next node in the list to append this thing. This dot next, call append with this being a reference to this node. So in the next stack frame, this is a reference to this node. It checks its next. It is null. And it says, oh, crap, I'm the end of the list. Not anymore, though, because I'm going to append something. And it's going to say this dot next equals a new linked list node with the value that we added and null to indicate that it is now the end of the linked list. And notice that this method returns void, so we don't get any feedback of whether it worked or not. We just have to test our code, make sure it is doing what we expect it to do before we start calling it, or start calling it and using it. So return type void, but we assume that it got added to the list, so we're going to make sure our code's right. Since we give you append, and I'm pretty sure I left all the methods in the code, in the linked list class that's included in the handout code for the project, you can just call append when you need to append. So the code's already here. You don't have to overthink that one. You can, if you want the extra practice, which I'd encourage. You can rewrite it and make sure you understand what's going on here. You really should make sure you understand what's going on here because this is one of the easier ones that you're going to have to write. But you can just use that code. And finally, find, before we get to min. Find, we want to find a specific value in a list. And when we find a value in a list, we're going to return a reference to the first instance of a node containing that value. Man, that sentence turned into a mouthful. So we're going to look for this value in a list by going node to node to node. And once we find that value, we're going to return a reference to that node containing the value. Now notice that there could be another node later on in the list that also has that value. So we're just going to return the first instance of it, which is common. Any find method that you have in a standard library for any data structures usually returns the first instance of the value you're looking for, or a reference to the node containing the first instance, if it's a linked list. And we want to return the reference. We don't want to just return the value. In an array list, you would return the index. We want to return a way to actually navigate to that part of the linked list. It's usually helpful in a linked list to have a reference to the node that you're concerned about, not just knowing that it does exist, that it is in the list. So this, we're going to do 2 checks, and the order is very important here. First, we're going to check if the value at this node equals the value we're looking for. And if it does, if this dot value is the value we're looking for, we're going to return this, which is a reference to the node that we're currently looking at. If this dot value is the value we're looking for, we're going to return this because this is the reference to the node containing that value. And then we're going to check if we're at the end of the list. If we're at the end of the list, we're going to return null. That's going to be our way for this method to indicate that we didn't find the value that we're looking for. That value is not in this list. The order is important here. It's a common mistake with linked lists in general to forget to check the last node. So if I did this check before the value check, I'm going to say, am I at the end of the list? If I am, return null. But what if the value is stored in the last node of the linked list? If you did this check first, you're not going to find that value. You're not going to find that. So we need to check the value first and then check if we're at the end of the list. So if we hit this condition, we're at the end of the list and we're returning null, that means this was already false. So the last node of the list doesn't contain the value we're looking for, and it's the last node, so therefore we didn't find the thing. This checks first, and the value we're looking for is the last element of the list. In the last node of the list, we're returning null when we should have returned a reference to the last node. So order very, very much so matters there. But we effectively have 2 base cases of our recursion. There's 2 different things that can stop the recursion. If they're both false, then we just move on to the next node. We make our recursive call on the next node. And then in the next stack frame, this is that reference to the next node. So we're looking for 3 in this linked list. Somebody asks, hey, can you find 3? First node says, yeah, let me do my checks. It checks if it's storing 3, it's not. It checks if next is null, it's not. So we hit the else, the recursive call, and we just pass the question off to the next node. So we make the recursive call, find, with this being a reference to this node now. This node does its checks. It says, oh, yeah, I got that value. I got it right here. And it returns it. We never even check this node. This node could have also contained 3. We don't know. We don't care. We just are looking for the first value for this specific method. We return it. We return a reference to this node. This node gets the return value of the recursive call and returns it. And our caller gets that reference to this node right here. Of course, with the whole memory diagram, we'd see I'd make up those OX numbers and everything, and you'd see that the caller got some OX number that matches this node, a reference to this node. With my kind of abbreviated memory diagrams here, I'm hoping everybody's at the point where we can understand this, that this is returning a reference to this node. What if we try to find something that's not in the list? Let's look for 8. First node says, this isn't 8. Next isn't null, so let me ask the next node. Next node says, this isn't 8, and next is not null, so let me ask the next node. This node says, this isn't 8, and next is null, so I'm going to return null. So this node says, nope, didn't find it. This node says, nope, didn't find it. We go up the recursion, returning from all these stack frames. Then we finally tell whoever called the find method, hey, we didn't find 8. Sorry, you're out of luck. Okay, any questions on any of that before we get into min? And we should have time to slow down and breathe a little for the min method. But any questions before we get into it? We got quite a bit of new stuff now after classes week last week and now linked lists. There's a lot of new stuff out there. If you didn't believe me that this class moves fast and it takes a lot of time, I hope you all believe me now. We're in the thick of it now. So let me have your questions. No questions. Everybody's super duper good on all this. Don't believe that. Don't believe you. Okay, I did slip one thing past you when we did the find method. I called equals. Am I allowed to do this? So we have a generic. We have some type T, which can be any Java type as long as it's defined by a class and not one of our primitive values. This can be any type. How can I call a method on it? I don't even know what type it is. How do I even know there is an equals method for this type? The answer is I just can. Every single type in Java has an equals method. Every single type in Java also has a toString method. So we got away with it on Monday with our recursive toString on the linked list because every single type in Java has a toString method. Whether you write one or not, even in the classes that you write, if you don't write a toString, you just get the default printing out the name and then some reference, at some reference. Same with equals. If you don't write an equals method, you get the default comparison of checking if two variables of that type refer to the same object on the heap. We saw this with equal. I didn't call dot equals in the example when we saw that before. But we did see that by default, you just get comparison by reference, which usually isn't what you want. And just like we did the toString, we can write an equals to override that default behavior, which we'll do eventually. We'll get there, but not today. So just not by pure chance, just by the way we design these lectures, we actually got away with calling toString and equals on a generic type. That value, that's going to be of type T. We don't know what type T is. It can be literally anything. But we actually can call toString and equals because those two methods happen to exist in every single Java type. Lucky of us. That's great. But we can't do much other than that. There's almost no other really useful methods that every single type has in Java. Hash code's one of them. I don't want to talk about it, though. I shouldn't even mention it. So what if we want to do something like min? So when we write the min algorithm, we need a less than operator, right? Well, not every type in Java has a less than operator. In fact, most of them don't. But when we have a list of doubles and we want to find the min value, well, double does have a less than operator. And I want to use it. I want to use that to find the min. I don't know how I'm going to find it with just equals and toString. That's not really going to help me at all. So how are we going to do this? And more specifically, more to the point, how are we going to do this with a linked list of ratings when I have a song? I have a song with a linked list of ratings, and I need to find a rating that was rated by a specific reviewer with a specific reviewer ID, which you have to do which is part of task 3, if you haven't read that one yet. So we have to navigate a linked list and check if this linked list of ratings has a rating with a specific reviewer ID. How are we going to do that? Not every method in Java, not every type in Java has a method called getReviewerID. In fact, almost none of them do. So we definitely can't call that from our type parameter. So we need another answer. Let's do this. So I'm going to create a new class, linked list of doubles. It's going to have a linked list node of double, and I'm going to abbreviate LL node, linked list node, again, space on the slide. This line was causing me trouble. This line got too big and was way over here. But we're going to create another class that contains a linked list node representing a whole linked list as an instance variable. And then we're going to work with that instance variable, which has a specific type. It has type double. So when I call getValue, it returns a double, because for this object, T is double. And this is designed to mirror the way you'll have it set up in your homework. Obviously, it's a little different. You have an extra layer of classes on top of your homework. But you're going to have a song class that's going to have a linked list node of ratings as a instance variable. You're going to have a way to add ratings, and you're going to be able to do some work with those ratings. Find if a reviewer reviewed that song, and eventually removing a review made by a specific reviewer, or rating made by a specific reviewer. So for add double, let me just talk about this quickly. I don't have a slide for it. To add a double, what we want to do is just call append. You already have the append method. We went over it in lecture. You have the code for it. Just use the append method that we gave you. So when you want to add a rating, you want to just append it, right? Again, I recommend that you, at the very least, understand what the append method is doing, because it's easier than the other recursive methods you'll have to write that were going to look something like this. But you just want to append. But there's one extra thing you have to do. Your linked list is initially going to be null. So you have to check. If it's null, then create a new linked list node and just set that instance variable to the linked list node. But once that exists, then you can call append. If you call append on null, you're going to get what's called a null pointer exception, and your program crashes. This dot numbers, if this is null, as soon as you say dot, remember, says your reference, I want you to take me to the object to which you refer. If you ask that question of null, which doesn't refer to anything, where do you go? Where in the heap are you navigating to? And at that moment, as soon as you type that dot, that's a null pointer exception. You're going to get errors, and your program's going to crash. So we want to avoid the null pointer exception, null reference exception. What are they called in Java? You want to avoid those null errors. So in your code, you'll have a lot of these checks, if null. We have those for the base cases of our recursion to see if we've reached the end of the list. We're also going to have them to check if the list is empty. This is effectively an empty list. So is the list empty? If it is, initialize the list to this as the new value. And then we're ready to call min. We add a bunch of doubles to this list. We're ready to call min, and we immediately have some problems. First one's easy enough to handle. Just like I mentioned, we're going to check if the list is empty. If the list is empty, we're going to return some value that indicates an error. Negative 1.0 doesn't quite make sense for this application. What if the min value of the list actually was negative 1.0? It doesn't really make sense, but I just want to get past this part and get to the juicy bits that I want to talk about. But you would have some return value that indicates an error occurred. Negative 1, again, doesn't quite work in this example. It's not the best return value for that to indicate an error. Usually negative 1 is if you're returning an int and the return value can't possibly be negative, then your negative 1 indicates an error. If you're returning an index in an array, for example, negative 1 means error, just typically, just by convention. So what we want to do is set up our recursion. We want to set up recursion to be able to navigate this list and find the min value. The problem is the min method doesn't take any parameters, and we would like two pieces of information that we're keeping track of when we find the min. One, what's the element we're currently considering? And two, what's the min value that we found so far? That should sound familiar from 115. You're iterating over a list. You're visiting elements one at a time, and then keeping track of the min you found so far. For a linked list, those two values become a reference to a linked list node. What node are we currently visiting? And the min value so far. Now, we got away with some of this in the previous examples because we leveraged this a lot, but we can't quite do that the same way here because we're not in the linked list node class. We're in this linked list node of doubles class. So we can't quite do the same thing. So what we're going to do is create a helper method that's going to have the values we want. The node we're currently visiting, a reference to the node we're currently visiting, and the min value we found so far after visiting all the nodes up to this point. And then we're going to call that helper method with the initial values we want, this.numbers, so the head of the linked list, as long as it's not null, and integer.maxValue. I like initializing my mins to this. Max value is the largest positive value that can be stored in an integer, so I know it's not going to mess up with my min calculations. Call the helper method, and then the helper method is going to be the recursive one. And we don't want to expose this to our users. We'll make it private. Users call this method. We use this just internally to help us do our recursion. We're going to check if we're at the end. If we're at the end of the list, we'll just return min. If we're not at the end of the list, we do our check. Is this value less than min? If it is, replace min in the next recursive call. If not, pass min forward to the next recursive